Okay, so the topic for today is short circuit analysis. Uh, so this must be like a review for all of us, including myself. So this is something that we have done during our college days, and for some of us who are doing this in our respective jobs, we may be involved in power system analysis. So uh, hopefully you'll get something out of this today. For those who are not involved in studies, uh, hopefully those will serve as a refresher. So this is myself. Obviously, I am a Filipino. Uh, I graduated from Bicol University, worked in the Philippines for the first 6 years of my career, 2006 to 2012. Majority of that, I worked in Manila for Fluor, Philippines. I was doing electrical design for mainly petrochemical and industrial. Majority of my experience is with that. And then I moved to the US. Moved to Canada in 2012 and now I'm here in the US. So now I'm working for utility for we're mainly designing transmission distribution substations and some renewable projects. And also, as of this time to time, I would also do some utility, no, some industrial design. So that's just some small information about myself. Okay. So let's begin with some introductory concept. So obviously, what is a short circuit? So the IEEE standard defined the short circuit as an abnormal connection of relatively low impedance, whether made accidentally or intentionally, between 2 points of different potential. And it's synonymous to the term fault. So that's why you'll see in books and in uh, webinars like this and trainings that the two are most of the time used interchangeably, short circuit or fault. Uh, but there is some small difference. I would say that fault is kind of a general term, um, while short circuit is mostly applied to phase phase faults, such as the three-phase fault or line-to-line fault. So a fault would, as we will see in the next slide, will have mostly 10 types. So causes of fault, so you have your presence of animals. This can happen in substation. That's why in substation you'll see we put some insulators in there and some kind of spacer to uh, prevent animals from jumping from insulators to conductors.
So voltage surges, so deterioration of insulation due to age. So as we know, our equipment, uh, it has some um, insulations as your, let's say your transformer, you have your winding insulation, um, switch gear, it's also, well, you have your, let's say your GIS, your gas insulated uh, switch gear. So those are forms of insulation that over time would, due to age, would deteriorate. Um, Voltage or mechanical stresses, so over voltages would cause damage also to insulation and would uh, eventually degrade the insulation that could cause faults. So these are some of the things mentioned here. I'm not going to mention everything. So, okay. Overduty equipment, human error, inadequate cooling. So this all goes back to um, different causes of faults, including natural disasters. Of course, when there are storms, um, overhead transmission lines and distribution lines could be broken and touch trees or the ground, and that could cause ground faults. So which are the effects of short circuit currents or fault currents? So currents are greater near the source. Obviously, that's because, as we will see later on, the the magnitude of impedance, which is the limiting element that determines the magnitude of fault, is smaller near the as you go nearer to the source. Voltage collapse uh, during a fault, the voltage will collapse to zero, depend or approximating zero value, depending on how the magnitude of the impedance. So that will determine um, how much value the voltage will sag or dip. The magnitude of fault currents impact clearing or tripping time of overcurrent devices. Yes, in protective relaying, which is not the main topic of this webinar, uh, fault analysis is performed in order to determine clearing or tripping time of overcurrent devices. So it's one of the reason for conducting short circuit analysis, by the way. And as mentioned, it can damage equipment. So I have listed here two reasons or objectives why we would calculate short circuit currents. So you have to calculate for the maximum fault current and compare it with the device interrupting rating. So but this is not the only reason why we would calculate for fault currents. But for this topic, for this webinar, we would concentrate on this two only. Which are the other reasons why we would calculate for short circuit currents? So you would also do that for, like I said, um, setting of your overcurrent protective devices. That's also needed for that. The other one is when you're calculating for your grounding study. That's another uh, reason why you would calculate for your short circuit current, because in grounding study you're interested to know how much fault current is flowing in the ground, especially in substations. We would conduct this grounding study, and there is what we call touch potential and step potential. So the objective of that study is to know and to determine how much current and voltage is expected to flow in should a person touches some of the metallic objects in the substation. So short circuit study or short circuit analysis is conducted in order to do that. And also there is what we call for grounding, uh, There's a type of grounding that we call effectively grounded system, uh, where um, there is no intentional impedance inserted into the neutral of your transformer. It looks like this. Let's say that's your transformer. You effectively or directly connect your neutral into the ground, and there is an IEEE requirement that relates to that, which is, I believe, your uh, X1 to R1 ratio should be less than or equal to 3. And there's another one, your, I believe that was the R1 value should be less than or equal to 1. So how would we know this? We'll only know this by conducting short circuit study, because it's one of the outcome of the analysis. You will determine your X over R ratio. So it's not really implied that you should do that, but the only way to learn or to calculate for that is to perform the short circuit analysis. So which are the sources of fault currents? The number one, obviously, is your electric utility system, which is the uh, greatest contributor of short circuit or fault currents. Motors, and especially in industrial facility, we have a lot of motors for industrial processes. So this this could add up. One or two motors, maybe not a big deal, but in industrial facilities, 80, it's estimated that 80 to 90% of the loads there are motors. So, your 1 horsepower motor, your 50 horsepower motor, 100 horsepower motor, they all add up and um, to thousands of amps. So when it comes to that, the contribution of motors is important to consider. Generators. Um, when we say generators here, this we refer to the local generators in your facility. Let's say again mostly in industrial facility, you have your connection to your utility as your main power provider, and then you have your local generators as a backup in case uh, you lose your power. So generators, well, if you think about it, what is a utility? Utility is just a collection of many generators. It could be, your traditional synchronous generators, could be your solar, could be your wind power. But nonetheless, if you think about it, they are just many generators connected to the grid. So, but when we say generators here in this context, we're referring to your local uh, generators, such as the one we're showing here in the photo. So, calculation. How do we begin to calculate for fault analysis or short circuit analysis? So we would look at system, and with well, there are a number of data that we need to collect, and one of those is the voltage level. Um, it's not just one; it's most of the time multiple voltage level depending on the location that you're interested in to calculate. So it could be most of the time from medium voltage up to your low voltage. So you have your step down transformer. So you'll have to gather that data. the available short circuit current from your utility. So that's one of the main things that you would want to know. So let's say you are conducting a short circuit analysis for your client. Uh, it's one of the first thing that I would ask. So do you have your utility fault data? So when I do this, there's a form that I would submit to collect this information from the client. And then the client would reach out to the local utility to get this information. Can be determined also from previous study, depending on how old the study was, because we know that fault level tend to generally increase over time for a utility. So the fault level today will not be, or probably will not be, the same 10 years from now. It tends to go up. So, and why would that be? If you think of why would it go up? So over time, as there are more and more customers, such as, more restaurants have opened, more industrial facility or factory has opened in the vicinity, in your area, the utility, because as we know, the substation has a limited capacity. It's designed to carry a certain amount of customer load. Let's say right now the substation is a 50 MVA substation. So based on that, there is a certain level of fault current out of that 50 MVA. So now let's say 10 years from now, more uh, residential areas have been established, more businesses have been established over the vicinity. Now the utility would have to construct, upgrade the substation, maybe make it 100 MVA, and that's the reason. Connect the grid, draw more power from the grid, and that's the reason why the fault current in that area suddenly increase. So, and this goes back to, I don't know if it's a practice. It's our practice in the Philippines, but here, every 5 years, businesses or establishments, especially the industrial facilities, are mandated by OSHA, the Occupational Safety and Health Administration, to reassess the system, to conduct another new study to determine whether their equipment, their devices, their MCC buses, switchgear, their breakers are still capable to withstand the available uh, fault current 5 years, or at the time. So every 5 years, you'll have to do this periodic analysis, and not just for short circuit, and uh, but also for arc flash. So I forgot to add that. So arc flash analysis is another thing that we do. So every 5 years, we'll have to do this arc flash study and relabel the devices, your panel boards, your MCC, your switchgear. You have to relabel it and update the labels, because we know that the fault current tends to increase, and what that means is the incident energy level tends to increase, and so we'll have to put that level a label to tell the personnel maintaining those equipment. And the objective ultimately in that analysis is to know what level of protective equipment they should wear when working in such panels or devices. And in order to do that, one of the things that needs to be done is short circuit analysis in order to conduct an arc flash analysis. So that's another application of short circuit analysis. So XR ratio. So this may not always be available, but it's one of the things that is necessary when conducting short circuit analysis, and we'll see why later it's important. So if not available, you can assume 8 to 12, but don't quote me on this. He said assume 8 to 12. So that's why I'm not gonna bother to ask my utility. I'm not gonna bother to investigate because Ryan said use 8 to 12. So please do your best to gather the data, and not even though I said here assume, but you know, gather the data. That a more realistic analysis is better. So NEC requirements. Why do we need to conduct short circuit analysis? So the NEC, or the National Electrical Code, which is the electrical code we use here in the United States, and I know our Philippine electrical code is patterned against the National Electrical Code. So I could assume, although I have not seen the Philippine electrical code in a long time, uh, I would assume that has the same requirement. So what does the National Electrical Code say uh, about that? So in section 110.9, it says that equipment intended to interrupt current at fault level shall have an interrupting rating at nominal circuit voltage at least equal to the current that is available at the line terminals of the equipment. It did not say conduct a short circuit analysis, but in order to know the fault current level at that equipment, let's say a panel board, you'll have to conduct short circuit analysis. So it's implied, even though it's not directly being said, it's implied that we have to conduct short circuit analysis. So that, and it's one of the objectives that I mentioned earlier, that uh, the devices, your panel boards, let's say, and your breakers should be capable of interrupting the fault level at that point. So which are the types of faults? So generally we have 10 types of faults. So you have your three-phase or three-phase to ground also, which is basically the same thing, because in a three-phase fault, all the phases have the same, assumed to have the same magnitude, and they are spaced 120 electrical degrees apart. So that means they would sum up to zero. So there is no ground fault current flowing to there's no fault current flowing to the ground. So a three-phase fault and a three-phase to ground fault is essentially the same. Then you have your phase-to-phase faults, which are three types. That's your AB, BC, and CA. And then you have your single phase to ground. So that's three cases. You have A to ground, B to ground, C to ground, and then you have your two phase to ground. That should be three cases also. That's AB to ground, BC to ground, and CA to ground. So you have essentially one here, three, three, three. So the generally 10 types of faults. So for the purpose of today's presentation, we'll focus on the three-phase analysis. This unbalanced analysis is somewhat difficult to deal with because we need a tool in order to calculate for such cases. And the tool, I believe you know which is that tool, which is the symmetrical component method. So that is the one we use as a calculation technique to calculate for uh, unbalanced uh, faults, which involve line to line and ground faults. So, but yeah, that's not part of today's training because obviously there's a lot to be said about that. I actually have, you know, side side plug. I have a separate training on that. Per phase analysis. So here is a representation of a three-phase fault. So you could think about it as a Y-connected fault. Why would that be the case? Well, what if I have a delta connected load? Well, that doesn't really matter because say you have, you know, you have, let's say that's your source. You have your load here, and it doesn't matter whether that's delta or Y connected. Let's say it's a motor or it's another transformer, and you have a fault here, three-phase fault. What is this connection? That's a Y connection. So that is this. So that is this. So you could think about it as a Y connected uh, fault, and so that makes this three-phase fault easier to deal with because we could calculate it as a um, per phase analysis, such as this one here. So with only the idea is we'll take the line to neutral voltage, we'll take one of the phases as um, the impedance to the voltage point in one of the phases, and we know that in a three-phase fault, we assume, even though in real life that's not perfect, but nonetheless, we assume because that's a good approximation that the analysis for one phase, let's say we analyze phase A, the magnitude in the other two phases, which are the phases B and C, are essentially the same magnitude, but they are just different in um, uh, phase angle. So same magnitude, different phase angle. So the idea, the principle holds true. So what I'm saying here is, let's say this is your phase A. That's a bad drawing. This is your A, this is your B, and this is your C. That's for an ABC sequence, and they are just spaced 120 degrees apart. So the magnitude is the same. So there's no need to calculate and analyze all the three phases. Just analyze one phase, and then we assume that all the three phases are having the same magnitude. So we now come to this per phase analysis. So if we draw the one line, let's say, it would look like this. Let's say this is your utility, that's your source. And then let's say you have your transformer here. And then obviously you have a conductor here. And then you have your OCPD here. and then maybe a bus, and then a load. So now we represented the source, the transformer, and the cable or conductor here, and the load in terms of impedances. So that is the general idea um, when conducting the short circuit analysis. We would convert the the different parameters, uh, your sources, your transformer, and your conductors and your loads. You convert it to an equivalent impedance, and then we would reduce the network into one single impedance, and that's what we call a Thevenin equivalent impedance. So let's say here, let's put some values for context. Suppose this is a 277 volts, line to neutral, and your source, let's say, is that ohms. This is in ohms, and let's say this is 0.85 ohms, and your conductor, it's, let's say, so, and your load is 2 ohms, let's say. So your current is simply your V over Z, is you would total your impedances. So that's 277 volts, divide the summation of your different impedances. So that would be 0.0041, 0.0085, 0.0034, and that would be, and then 2 ohms. 2 ohms. So the resultant current, if we do this calculation, that would be 137 amps. Now, consider here in the next slide that there is a fault here, and that would be somewhere, let's say here. There is a three-phase fault here. There is a fault. Now, as we can see here, this is essentially shorted. So doing that same analysis, our our new value for our current, that will be, again, but now this time this is excluded from the calculation. Now you have your sources only, which is plus 0.085 plus 0.34, and now your current is, so there is a huge jump difference between a normal loading condition here, which is 137 amps, versus a faulted condition, which is what we see here is 17,313 amps. Huge difference. And why is that? That is mainly because in a fault condition, you essentially remove your load, and that's why the name, if you think about it, short circuit. You, the fault current, the short circuit current has taken a um shorter path. So previously it would circulate including the load. Now it does not. It bypasses the load. It has taken a shorter path. So the name the name kind of makes sense. The name makes sense physically when you think about it. So that's how the concept is. That's generally the concept. So so which is the flow of short circuit current. So now when you're conducting short circuit analysis, let's say this simple system, you have your uh, generator or your utility here. So you are interested to know the fault current at your devices. Let's say here, your MDP, your PP1, PP3, and PP2. So these are separate calculations. So the flow of the short circuit current will be like this. So it flows down from the source and flows down from the source going to the faulted uh, location. In this case, uh, let's say here. So and now here, let's say that's another analysis, another calculation. So it would go from the source to here. So like that. Or let's say here, so it will go like this. So the the flow of the current comes from the sources going to the faulted point. And the source, as we mentioned earlier, the major source is your utility, which is this. Okay, that's your utility or your generator. Or that well, that could not be a motor, isn't it? So your motor will be, where later on we'll look at it, is connected as a load. That can contribute also to fault currents, but we'll see that later. So when dealing with when doing short circuit analysis, we will have to deal with complex impedance, and we have to perform addition, as we know, in order to get the total impedance. So here is an XR plane. It's a complex plane. So down below here, we have our R resistance. And here on the vertical, we have our X, our reactance. So Z is our impedance. And we're normally given the XR um, value in your transformer comes with your XR value. The transformer nameplate itself would show that. What else? Your utility, like I said, really try to get the actual um, XR value from your utility. Your cables, as we will see later, you can get that values from your um, the manufacturer data sheet. Good thing now, um, you know, because of the internet, this information are relatively easy to get with just one Google search. You'll be able to go to your manufacturer uh, website and get catalogs from there. So, and this is how you would add your impedances. So your, let's say your Z1, impedance 1, C2, C3, impedance 2 and 3, you would add them tip to tail. So in consideration with their impedances, their angle, uh, which is also you can determine from your um, XR value, not just arithmetically add the magnitude, because that would yield to a wrong value. So here, let's say you have you have your X1, R1, This is your R2, that's your X2, and your R3 will be somewhere here, R3, X3. So your Z total is essentially your R1, R2 plus R3, uh, plus X1 plus X2 plus X3. I know you all know this. And raise to the 1/2 because we need to get the resultant. So, and that will not be the same if we just add them arithmetically without considering the XR or the phase angle. Conductor impedance. So conductors, there was somebody who asked me some time ago about my uh, technical engineering report for my PEE application some time ago, way back 2011. I mean, somebody asked me, I think that was 2, 3 months ago, because he saw my PER. I made it available in my website if you're interested to get that. So he said, I noticed that you did not consider conductor data. Well, why is that? I said, that's because of age difference. I probably was lazy at that time, did not bother to put the conductor data. So now that uh, you're watching this, I'll take this time, this opportunity to tell you that uh, if you are planning to take your GEE exam, I highly encourage you that when you do your ER report, gather as much complete information as possible, including your conductor data, because it makes a lot of difference in the fault current calculation. It really does, especially in the lower voltages, because lower voltages tends to have smaller conductors, which tends to have higher uh, higher impedance value, which means it limits the fault current greatly. Meaning, if you don't use, if you disregard, if you neglect conductor impedance in your short circuit calculation, you're gonna end up with higher fault magnitudes in your analysis. And you'd say, well, this is good, isn't it? Because I am safe, you know. But somehow that's true. But that is oversizing your equipment. That's kind of oversizing your equipment, I would say. So try to gather as much realistic data as much as possible to to get a more clearer picture of your installation as close to the real thing as possible. So get the conductor size and type. And there are tables, published tables from the National Electrical Code, from the IEEE standard, and most especially from the cable manufacturers themselves. They have this information readily available for us for free. You just download it. So get the data, I would say now. So how does the conductor size affect your calculation? Well, like I said, higher, bigger conductor size, as we know, tends to have smaller impedance. type, the aluminum, as we will see later on, aluminum, copper, conductor type, different value also of resistance. What do you call that? Coefficient of resistance. So different. So obviously copper has a much, when I say much, a lower resistivity. So number per phase, this affects your calculation, of course, because when you tend to parallel your connection, you're lowering down your impedance. Length, obviously, when you have longer conductor, that tends to increase your impedance, so that limits your fault current. Insulation type, what is this? So the main effect of insulation is really on the X part, on the reactance. So consider, let's say that is your conductor, and this is your insulation, and this is wrapped around another. That's bad. And that's wrapped around another insulation. So you have your uh, 3-core cable, let's say. So the thickness of your insulation affects your reactance. And why is that? Because the thicker your insulation, the greater separation of the uh, the the conductor from each other. So you'd see that if we take out the insulation, the the metallic part gets separated farther apart as you have thicker insulation. And we know that mutual inductance and self inductance formula, I do not have it by memory now because that was a long time ago from our college days. We know that it is affected by what we call the GMD and GMR, your geometric mean radius and geometric mean distance. So the thicker your the thickness of your insulation affects that GMR and GMD. So that affects in turn your inductance, your L, which affects your reactance, because we know our reactance X of L is equals to 1 over 2 pi FL. So this one I have not forgotten yet. So the thickness of your insulation affects ultimately your reactance. Again, like I mentioned, the number of conductor per phase will affect your bring down, because as we parallel, what happens to a parallel impedance or resistor, it brings down the impedance, because what C total now is equal to 1 over C1 plus 1 over C2 and so on, raised to the -1. So it brings down as you add more parallel conductors. And in relation to this, if you think about your utility, and we will look, oh, well, we're gonna pass through it later, the utility. It's related to the utility, which like I mentioned earlier, what is a utility? It's just a collection of n number of generators. So as you have more and more generators connected to the grid, which is essentially like this thing happening here, paralleling more and more impedances, because we express utility as an impedance when we do short circuit analysis. It brings down the value of the impedance of the utility. Same thing with what's happening with the conductor. You think about it. So that's that. So here is a table from the IEEE standard. This is just for illustration purposes only. I'm stressing to use the actual data. So just looking at it, let's say here for 4-aught, you can see the resistance for steel, aluminum, and PVC or plastic. So you can see that for steel and aluminum, the resistance is the same. It's higher when you're using PVC. Why do you think that is the reason? Well, if you think about it, what happens when a conductor is energized? I mean, there is a current flowing in it. So when the conductor is energized, that means current is flowing. And we know that current creates or generates heat. I squared R times T equals heat equals energy equals watts. It heats up your conductor. Now, when you use a metallic conduit like steel and aluminum, what does that do? It heats up your conductor because metals are good conductors of heat. That means it further heats up your conductor because the heat dissipated by the conductor is contained in a metallic conductor. That's why your resistance is higher compared when you're using plastic, because plastic is not a good conductor of heat. So it heats up your conductor, and we know that the resistance is also affected by um, temperature. Now, looking at the X value, the aluminum and the plastic are now the same. Let me remove that. So the aluminum and the plastic are the same, and they are lower, while the steel is higher. What's happening here? So the aluminum is not good when it uh, comes to conducting um, magnetism, unlike steel. So what's happening here is that, again, when a conductor is energized from our Lenz's law, it generates a magnetic field around it. That magnetic field would interact with the conduit, obviously, because its conductor is inside the conduit. So a steel is a good conductor of um it's what's the it's a ferromagnetic material. I think that's the term. So it conducts a magnetic field, and so it interacts with your um, inductance, because inductance again is influenced by um, magnetic field. And so you could see that for steel, the reactance is higher versus aluminum and plastic. So yeah, I hope that's something that's kind of useful information for you. So THW, RHW, RHH, and different kind of insulation, different kind of values. We're not gonna go through that and spend too much time. So okay, let's do a simple problem here for conductor calculation. So for this problem number 1, we have a 480 volt Y 480 Y 277 volts, and there is a 45,000 amps uh, short circuit amps, and then we need to, based on the National Electrical Code 110.9, we must specify a new panel with sufficient interrupting rating, and the HTP3 is being added. This is a new panel, let's say, and we have a 75 feet 4-aught conductor here with THHN insulation, let's say. So for MD, our choices for PP3 is 22 kA, 42 kA, and 65 kA. So how do we deal with such calculation? So we will, like mentioned earlier in the per phase analysis, we will reduce the network and conduct the analysis in this manner. So we will get the utility impedance and you will get the conductor impedance, and then based on that, out of that, we will calculate the pole current. So, and I have some wrong labels in there. So anyway, so our impedance, our short circuit amps is 45,000. And then let's assume the XR value to be 12 because it's not given. Like I said, try to get that. So our V line to line is equals to 480, which leaves us the V line to neutral is equal to 277, 277 volts. So our source impedance, source, this C sub 1 is simply our voltage divide 45 kA, which leaves us this value. I already pre-calculated it, so we're fast. X1, we'll get our X1, which is essentially equal to Z1. So again, our triangle here tells us that this is your Z1, that's your X1, and this is your R1, right? And this is your power factor angle, which is, we could say tangent of theta is equals to X over R. And in this case, we know this to be 12. And this is equal to, then we could get theta arctan of 12, which is what? 85 degrees. So that's how we obtain our angle. So meaning our x, what is x in relation to z1 is essentially sine. So c1 sine theta. So whatever the value of our z1 times the sine of 85.23 degrees, and then we'll obtain eventually this value. We'll just shortcut it in the interest of time. So R1 in the same manner can be obtained by, well, you don't have to use trigonometric function. We'll just divide x1 by X over R ratio. So that means our R1 is simply this value, which is, so they're very small numbers. So in that same manner, we'll get our conductor impedances. So X of conductor is given here on the table. What did we say? Our impedance, we're using THHN, and we're using 4 aught. So here, here. So that is what we are going to use. And remember, that is in milliohms per 100 feet. So meaning you will have to divide that by 1,000. That will become 0.00534 and 0.00393. And that's here, that's per 100 feet. And then we're gonna multiply that by whatever the length is, which in this case is 75 feet. So our X sub C is now 0.00393 ohms per 100 feet times 75 feet is equals to 0.002948 ohms. These are all in ohms. So in the same manner, we'll obtain our resistance, and the resistance is 0.00534 per 100 feet times again 75 feet, and we'll get. Now, the next step is to add Z1 to get the C total. This is my Z1, this is my Z sub C, which is the conductor. So my C total is essentially Z1 plus Z of conductor or CZ. So again, using the vector addition, this is essentially what we did earlier, R1 plus RC squared plus uh, X1 plus XC squared raised to 1/2. So if we do that, now we'll obtain a shortcut so that I don't have to show you every step of the way. Our C total is going to be 0.010143 ohms. So now that we get our C total, we can now get the fault current here, which is essentially my short circuit amps is equal to the voltage divide the Z total, which is this 0.010143, and that becomes 27,310 amps. Then I could get my new XR, X over R. Let me just call that X over RT total. So to do that, we simply divide the total XT and the total RT. So that is simply let me write that down. My XT is 0.009082 divide 004516. And now my new XR is this. So I got my short circuit amps, and I got my new XR value for a fault here. So that is short circuit analysis in the most basic um, idea, like what we have seen in the per phase analysis. So now the question is, you have 27,310 amps, and then here are your choices. You have 22 kA, 42 kA, and 65. It's obvious based on this calculation that 22 kA is not going to make it. I would say pick 42 kA. That's the next candidate. I mean, you can get you can specify 65. Why not? It can satisfy also. But remember that the higher the interrupting rating of your devices, uh, when we say interrupting rating, that pertains to your uh, overcurrent devices, to your breakers, to your MCCBs, and to your fuses. And then for your panel boards, your MCC, we generally call that duty rating. Uh, the higher the rating is, the more expensive. So you do not just randomly say I'll pick the highest one, because you may be spending more money for no reason. So select the adequate. I'd say select the adequate rating for the application, for the right application, which is the why we're doing this calculation, so that you could select the proper rating without uh, being too conservative and spending money unnecessarily. So some terminologies here. What is an available short circuit current? Is the IEEE defined it as the maximum possible value of short circuit current that may occur at a particular location, assuming that no fault related influences such as arc impedances are acting to reduce the fault current. Yeah, this arc impedances, they are generally very high and they're very difficult to calculate. So in fault analysis, we normally neglect the arc impedance, because it's very difficult, I mean, if not impossible, to tell what impedance that arc would be, because it can be influenced by any number of uh, cases. So, and then just to be on the safe side, neglect the arc impedances. That's what the IEEE tells us as a recommendation to conduct the short circuit analysis. So okay, so now showing here some waveforms. I know most of us have seen this. So we have this what we call symmetrical AC waveform that we are very familiar of. So a current or voltage magnitude that oscillates between the zero value to the positive maximum and to the uh, negative maximum also. You know, 0 plus 0 goes back to minus, and uh, all that. So this curve is a totally offset AC waveform. Notice here that the zero is here, and this waveform did not cross the zero boundary. It's in the positive uh it's in the positive quadrant only. So it oscillates between 1 per unit and 2 per unit. Why we are showing this? This is related as to, and we will see later on, to the uh XR value of the fault. The higher the XR value of the fault tends to create a higher offset in the waveform, and we will see we will see the formula why that is. So here's a decaying symmetrical AC waveform. What is this really? So um we mentioned that there are generally three sources of fault, which is your first, your utility. You could think of your utility as a very strong source like that. It does not decay with time. It does not diminish. While your motors would last only a few cycles, and later on it's gone. 4 cycle, 2 to 4 cycle, 4 cycle at the most. And so when you add up your motors and your utility, this is what you get. So in the beginning, if you look at here, in the beginning, you have the combination of your utility and motors and maybe your generators together. That's why you have this symmetrical waveform that is higher in peaks. And then around here, this part, as you go to the right, your motor contribution may have died off, has decayed, and now you're left with your utility contribution. So that's why we have this decaying AC representation. Now, what about this decaying DC waveform? This is related to the XR value of your fault. And like I said, the higher the magnitude of your, uh, the higher the value of your XR, the more prolonged this decaying DC, and we'll see that. So this is the asymmetrical fault current. That is your AC superimposed with your DC. So as you're here in the beginning, when you have your DC, you can see that the peak here has exceeded the 1 per unit. And then as it decay, like this, looks like that.
Increase kunyari.
Now, at this point, you only have your AC component because the DC part is gone. Now you have this part now is symmetrical, as you can see. So we already talked about this in the per phase analysis that I showed earlier. Let me try to. Oh, I thought I removed that already. Wait a minute. Give me a second here. Yeah, I thought I removed that already. Anyway. Give me a second. Probably use the old slide. Give me 1 second here. You wanna take a break? 5 minute break, Sir Michael.
Yes po.
Okay, I'll switch to the new slide. Sorry about that. So let's take a 5 minute break. I think it's just about time to take a break.
Sige po, sir.
Okay, so just continue. Please let me know if you're able to hear me.
Yes po, sir. Okay na po.
Thank you. Sorry about that. I tried to trim down this training because, I mean, this slide, because there's a lot of slides. Tried to trim it down. I thought I saved it. So still showing a lot of slides. So anyway, we'll just pass through uh some of this because in the interest of time, I tried to, like I said, trim down the training. So let me, somehow it did not save. I don't know where the other exercises went. Okay. We could do, okay, I know what I will do. So we'll go through the slides and then let's do the some of the exercises in the notes. Okay. So okay, we'll just quickly review this. Was trying to remove this from the training because so many slides. The instantaneous value of voltage and current, we know this from the old days. So the value is, as we can see, if I have tabulated here on the right side to show us the equation, and then some of the derivation here. We know that this is a periodic function, and that average is this. Just one of the concepts that we are interested in. Under root mean squared. Also, we know the value to be this 0.707 or 1 over square root of 2. And the significance of the RMS when sizing your specifying your equipment, when you calculate your surge circuit current, uh, we normally talk about your RMS value, but there are cases where you're interested with a peak value of your short circuit current, and that is in what we call the first cycle duty, because in the first cycle the short circuit current tends to be higher because of the DC offset. So during the first cycle, you have your DC offset. You have all of the contributions come from your utility and from your motors. So that part, and when we go here, we have this. Well, this is a general equation, and when that is solved, when we calculate for that, this is your equation. So looking here, you have two parts of your equation, which is this one here on the right. That is your symmetrical part, and this is your this part right here on the left. That's your decaying DC. Eventually, the DC will disappear. But why is the DC of interest for us? Why bother if it disappears after a few cycles? Why bother with that? Because the reason why we're interested with that is because your devices, your fuses, your low voltage breakers would operate during this first cycle. Even the new relays now, the relays, numerical, I'm talking about numerical relays. These relays are now very fast, and they would be able to make tripping decision within one cycle or less. Meaning, during this time period, your relay, your breaker, your fuses are seeing both the DC part and the AC part of the fault. So, and then your fuses and your MCCBs and your relay, your fast relays will try to make tripping decision during this time. So it's important to consider the DC part. So here is that your DC part decays during this time, and this is for an XR ratio equivalent to 7.5. Now, looking at the decaying DC part and its effect, I have tabulated here. Don't need to look at all of the details here. We'll just try to to understand the effect. So for an XR ratio of 7.5 here, this is all 7.5. This is 12. I have tabulated here that you can see that for 5 cycles, your value is 0.0152. That's 1.5%. While here, for the same time period, if your XR is 12, that is 7.29% versus what is the 1.52%. So you could see immediately that there's a huge difference. So as your XR value tends to be higher, it takes a lot longer for the DC part to decay, to eventually be gone. So why short circuit currents are asymmetrical? Again, so here, we mentioned that the DC current is decaying here. You can see now clearly that we have superimposed the DC on top of the AC. So that is essentially this one here, the AC symmetrical plus your DC, which is decaying over time. If you add those two values, you can see now that your total uh, current magnitude is decaying over time like this. And now at this point, you no longer have your DC. Now you only have your AC part. Uh, I've shown it here just for uh, context. Total offset, totally offset AC waveform. What is this? When you have a when you have a purely inductive circuit, your your waveform would tend to oscillate between 0 and 2 per unit. It does not go through the negative uh, region, just like this one. So here, for a much clearer view, this one here, this is wrong. This is purely resistive. So as you can see, it's a purely resistive. Oh well, that's both purely inductive circuit, but fault is occurring at the uh, voltage peak. So we know that for an inductive circuit, the current lags 90 degrees. So look here, the red one is your current, and the blue one is your voltage, as you can see here. So if your fault occurred at a voltage peak here, this part, fault strikes there. So the tendency is for the fault current, like I said, to lag 90 degrees. So this part, that's 90 degrees. Oh, that's 90 degrees. So current is lagging behind 90 degrees. So as you can see, there is no offset if the fault happened at the peak. While here on the right graph, when the fault occurred at the voltage zero crossing, zero magnitude here, the fault strikes here. Now, because the fault current uh, needs to lag the voltage by 90 degrees, and it's physically impossible to make that uh, stepwise change in zero time. That means, because physically, in order to achieve an instantaneous change in current, and we know that in an inductive circuit, uh, the inductor opposes sudden changes in current. So that's why you have this offset. So you can see here the current is supposed to lag the voltage. If you trace down this, that part is your 90 degrees. That is that's the physical explanation why in an inductive circuit you have this decaying DC. And let me go here. So what is the significance of this decaying DC anyway? So we need to account for the peak magnitude, because like I said, the decaying, the DC part added up would add up to create a much higher fault magnitude, and uh, that influences uh, of course, your thermal energy will be higher for once, and then your electromagnetic forces exerted on your uh, mechanical parts of your, let's say, your panel. So your panel board is constructed like this, let's say, right? And then you have this, uh, right? And they have uh, mass bracing that we call. So, oh, that one is wrong. So they have bus bracing. So during faults, the magnetic forces is so high that it would vibrate vibrate your your equipment, creates very strong forces. And so if your let's say MCC or your devices is not designed to withstand such high magnitude, then it would buckle up the metal. It would uh, distort your uh, connection, your physical connection. And to illustrate that, let's see here. Is it going to play? Oh, here. Look here. Uh, you see that? So that's the fault. That's the effect of a fault. So it twists your conductors. So imagine that happening inside uh, your your panel board, your MCC, inside your transformer. Your transformer has also um, has also connections in there to secure the windings of your transformer, your core. They are fastened in place so that they don't uh, move. So imagine that amount of mechanical force happening during fault. So that's why we have rating for our devices for which what we call bus bracing rating, which is the limit how much fault current your, let's say, your panel board or your MCC can withstand. So that's the significance of why we need to consider the peak currents. Okay. So some application here of asymmetry. So faced with the largest of the fault current peak is of particular interest, as we already demonstrated. Um, we need to account for that peak current, adds which accounts for your decaying DC. For your breakers, the application of asymmetry, especially here in your low voltage breaker, as mentioned. So that one, because they act uh, during the first cycle. Your high voltage breaker also needs to be rated for your asymmetrical current magnitude. It's also significant. Fuses also on transformer, as mentioned. Okay. So here is that. This is the uh, here is another illustration that is related to decaying DC. So again, assuming here that the fault occurred, this is your uh, voltage, right? It's your voltage. So assuming here that the fault occurred at the zero uh, crossing, so zero magnitude, when the voltage is at minimum at zero value. Here, your current has to lag 90 degrees. And when you look at your decaying DC here, your decaying DC, that is exactly the same here. So this value is the same as this value here. They're the same. So that is the physical explanation of your decaying DC. Because like I said again, in an inductive circuit, current cannot change in zero time. Uh, it would take an infinite voltage, which is not physically possible, in order to achieve that. So that's why uh, your current offsets upwards. And as you can see, as as this as this one decreases, and so the value of the decaying DC also decreases with the same in the same manner. So these are just some IEEE equation approximation for the half cycle. They even have the IEC here, which is not of just for comparison, but it's not really of interest. I mean, for me, I don't deal with the IEC. Some more equation here. So here is kind of a representation showing us that here you don't need to read everything. So for an XR value that is increasing, as the XR value increases, you can see 0.5, 1, and so on. The time to peak also increases. And the DC component here also increases. So when you see at 20, there is about 85.8566, while a 1000.99, almost 1 per unit. And when you add that up with your AC, which is also 1 per unit, so you have almost 2 per unit when you have a 1000 XR ratio. But a 1000 XR ratio is like saying it's a perfectly inductive circuit, which is not physically, not realistic. Uh, out there in our substations, you'd see 15 to 25%, at 15 to 25 XR value as the common value. For distribution, 8 to 12, 8 to 15 is fine. So the more you go to the higher voltages, to the transmission, high voltage, extra high voltage, the XR ratio tends to go higher. Going to the lower voltages, because you have more resistive part now, you have your lot of cables, that brings down your XR value. Okay. So here is some comparison just to demonstrate that XR value equals to It looks like this, the graph. So when your XR again is infinite or it's purely inductive, it's oscillates at 0 and 2 per unit. When you have a purely resistive circuit, no inductance, it's a perfect, there is no DC component, essentially. Here is that's wrong, that's not 0. So here's a 15 XR ratio, 25. So this is 1000, as we have seen. So bottom line, your XR ratio is of great interest. Here is some comparison between the half cycle peak equation. I'll just trim it down and send to you, so you don't have to worry about that. So RMS short circuit current equation. Now we're down to the RMS equation, which is just basically a derivation of what we have here. So I'll just send this to you for analysis. It's taken directly from the IEEE standard. So which are the steps for conducting short circuit calculations? You have to prepare your one line diagram. Obviously, you may have to conduct short site audit. If the installation is existing, well, you may have to go to the site and gather, especially with the old installation where they don't have drawings. It's challenging to do that. You have to go to site and try to look at the panel board, take pictures, uh, jot down the information, and then when you go back to the office, you have to model the system, put all the information that you have gathered, and then nowadays we use software because it's a tedious task. Imagine doing this by hand, and you have hundreds of devices and hundreds of panel boards. If you do that by hand, you're gonna consume the whole month, maybe. So we do this by software nowadays. You're lucky if it's a new installation, because you don't need to go to the site because there's no site installation yet. So you're just gonna pull up some drawings from the engineering design. So you're gonna go get your panel board schedule, your load schedule, cable schedule, and things like that. And software such as, let's say, ETAP, SKM, what else? EC Power, they have built-in databases coming from, they take this information from the manufacturers. So they would input let's say for cable manufacturers, they would take that information, put it in their database. So you don't have to check and look up this information by yourself. So, pick from that database, and the information is there. The value of the resistance, the reactance, etc. is there. For motors, they also have the information there, uh, etc. For all of that different devices, transformers, utility. Of course, you have to get that information from your utility. So this is the same representation that we already showed earlier. So per phase analysis, and single phase diagram. So per unit calculation is another concept that used in short circuit analysis. It simplifies the calculation, especially. So earlier we did the example with the cable, right? And we use ohms. So that's the ohmic method. Now here, the per unit method is essentially expressing uh, the quantities such as impedances, uh, currents, what is voltages. You would express that into a common base, and that makes it easier, especially when you have transformers, because in transformers, the impedance and the current is different in one side than the other side. So it makes it hard to calculate with all these transformations, and you have multiple transformers in your facility usually. So uh, using this per unit analysis makes it easier. So you have to use a common base. Normally, a 10 MVA is what is preferred when it's an industrial um, facility, and a 100 MVA when it's in the utility application. There's really no right or wrong here. It's just a preference. That's just how the industry evolved. You can use any base if you want. This 10 MVA and this 100 MVA is just common practice recommended by the industry. So if you look at ETAP, when you open up ETAP, ETAP is always in the 100 MVA base. So whatever base you would choose, eventually it will, as long as the calculation is correct, it will still arrive at the same final value. So it does not really matter. So how do you convert from ohms to per unit? So here, your ohms is divided by the ohms. Here, the C ohms is the ohmic value of your device or your equipment that you wanted to express as a per unit value of a chosen base. So this is the formula. And if you think about it, it's essentially equal to C in ohms of your device divided by C of a chosen base. And what is C is essentially V squared over S, right? Which is V squared over where S is your apparent power, which is your MVA, and your V here is in kV. So that's why uh, when you express it like this, that's essentially what kV squared over MVA, and then your MVA goes up, and you're left with your kV down. So that's why your MVA is here at the top. So normally your devices such as a transformer is already given in per unit. The impedance is already given in per unit, not in ohms. So you'll have to convert that into your chosen uh, base. So you have to select a common base, And the formula is this. Let's go here. Combining equation. So it's just some derivation here. And this is for amps. And this is for Z, for impedance. So now you can see why we have kV squared here. If you choose kVA, then you multiply 1,000. If you choose MVA, then you don't need that 1,000, because here you already have chosen kV. So we'll have some example here. So okay, so this is an actual nameplate. So this transformer has 6.6% impedance, 34,400 to 12,470 volts, and then 3,750 kVA. So we want to convert the percent impedance. By the way, percent impedance and per unit, they are just basically the same, but expressed in different ways. So percent impedance, as the name implies, is in percent, while the per unit is in kind of decimal. So a 6.6%, as you can see here, to express that in per unit is to simply divide that by 100. So now you have 0.066. So to convert that into the ohmic value, now we use this formula here. The Z per unit times your kV squared divided by MVA squared. So now the resultant is 20.83 ohms. So that's the actual ohmic value. So if we wanted to express this in a different base, such as let's say 100 MVE base and a different voltage, 34.5, let's say. Now you have to multiply that with using this formula here, MVA common base times kV of the equipment divided by the MVA of the equipment. So basically adding up, replacing it with the values. Now we have 100 here for the new base, and 34.5 as the voltage base. Now the resultant is 1.75 per unit. So it changes your per unit value, but it did not change the actual ohmic value. So that's just one thing to remember. So just some kind of reminder here. So sometimes it's confusing. I get confused at that sometimes. So the basics, I said, go back to the basics here, is to what is Z? Z is essentially V squared over S, right? So, and what is per unit? So essentially that same Z divided by a Z of choosing base. So at a new base, you could say that C per unit new is equals to that Z, which is in ohms. This is ohms divided by the new base, obviously. But what is Z? The Z is essentially the C per unit before times the base before, which is the old one. So it's just basically rearranging this equation here to make it the C in ohms. This is equals to C per unit times C base. Now this base will become your old base here. That's why you're calling it old now this time. And now because you have chosen a new base, then you'll have to divide it with the new base. Essentially coming back to this idea here. Except now this time, you have this old base and new base. And you have to do that because the reason is you have to go back to the ohmic value of your impedance, because remember your ohmic value does not change, only the per unit value changes depending on which um, base you have chosen. So that's the kind of idea to remove my confusion. And of course, now the your base, you can express your base also in terms of MVA. Here, this next iteration of the formula is essentially this one, right? So this is your MVA, which is what essentially equals to V squared over S. So that's why we have that, and same thing for the one here up top. And so if we further rearrange this equation, now we have this the S, or the MVA new is up top, the MVA old is below, the voltage old is above, and the voltage new is below. It's basically rearranging the equation. Okay. So this is the Thevenin equivalent circuit, which we already have looked at earlier when we solved for the per phase analysis. Let's just review here. Technique is to reduce the the network. So here, first you have your voltage sources and your ohms, and then your fault of interest is here. So you're looking there, and now that's why you have this. You're looking back to the source, and so further reduction of the circuit, as we can see here, becomes now one ohmic value, and it's been replaced one by a further reduction of the circuit. You have now 1 voltage and 1 ohms, which is essentially the progression when you do the short circuit analysis. Is you do this for every point of interest. When I say point of interest, for every, whatever point you're trying to analyze. Well, let's say you have your MDP here. Well, you have to do that for the MDP, and you have another panel here, then you have to do that again. So as you can see, it becomes really tedious as you have more and more devices. So how do we model equipment? So these are what you get normally. So this snapshot is from SKM. So this is what we get normally when we request from the utility. So they will give you this a three-phase on line to ground fault current and XR. See, XR is here. So they will give you that in usually in amps and XR. Sometimes they will give it to you in MVA and XR, and that's the same. And of course, the the voltage level. So that's this one. So here you have selected your 100 MVA base. Oh, there's a question here. How do electric utilities obtain their short circuit data, such as the available fault current and the XR ratio at the point of their connection? How do they know? How do they determine that? When you request that, where do they get that from? Anyone? It's my first question to the group. While I look here. Where does the XR ratio come from? So the XR ratio and really the fault current comes from an elaborate and very big uh, database. So essentially, the utility would try to model all of their system. It's like your ETAP or your SKM model. They would model everything, and when you ask for a fault level and XR value at certain location, let's say point A, they would extract that from their database. Essentially, just like just like you and me doing the short circuit calculation, essentially. So the short circuit data and the XR ratio is essentially predicted value by the utility. It's not something that how you call this. It's not something that you would measure on that uh, particular point. It's a predicted value by the utility based on their model uh, system. So synchronous machines, basically we have generators, condensers, and motors. So this is another. I mentioned that uh, motors is one of the contributor of short circuit current, and majority of the time, probably 95% of the installation, maybe more than 95%, are induction motors. And the synchronous machines is another one. And the only difference, and I don't have that uh, drawing here, you'd see it in some books that synchronous machine they would try to model like this, let's say, and induction they would model it something like that. So saying that an synchronous motor contribution to the fault current would last around 4 cycles, while an induction motor would begin within 2 cycles. And the reason for that is the synchronous motor they have their own excitation, uh, external excitation here, while the induction motors they do not have a separate excitation device. So the moment that the fault has occurred, the voltage, the terminal voltage collapses to zero, which means induction motor loses its excitation immediately, and that's why the magnetic field, the electric field, collapses immediately, and so that's why it's not able to sustain its fault contribution. While on the other hand, since the synchronous motors have their own separate excitation device, that's why the fault contribution would endure for a few more cycles. So that's the explanation why there's some difference. That's the kind of main difference as far as fault contribution is concerned between induction and synchronous. Some terminologies here. So X double prime is your direct access subtransient reactance. These are IEEE terminologies. X prime, XD is your kind of steady state. The only differences here is where do you apply this? This X double prime is you would apply it in the half cycle network. This is generally smaller than your this reactance is the smallest value of the three. So while the direct access is up to you would apply that for your interrupting calculation, which is generally it's divided into half cycle, 1.5 to 4 cycle, and then 30 cycle. So these are three analyses that normally you'd see in softwares. So half cycle, all contribution, all motor contribution are there, and then 1.4, 1.5 to 4, induction is gone. Maybe you have contribution from synchronous motors, and then 30 cycle, all motors gone. You only have contribution from your utility. So in order to account for that time varying contribution, what the industry has adapted is to use time varying reactance here. So this three is that because during short circuit analysis, we assume the voltage to be 1 per unit, right? So, but in reality, actually what's happening during a fault, the voltage collapses to zero. So it's actually the voltage that is collapsing. So in order to make the analysis easier, we keep the voltage at 1 per unit, and then we vary the reactance. So it's kind of, just to make the analysis easier. So if you think about it, let's say during half cycle, the typical value 0.2, let's say you have five times the value. And then during the next cycle, which is the 1.5 to 4, you have a higher reactance. Let's say, what's the easiest number? 0.25, just to make it easy. So now you have 4. So it's easier to do that, to vary the impedance instead of varying the voltage. That's just the explanation of that, why we have these different values of reactances for the same motor. It doesn't make sense to me before though. Why? It's the same device. Why do you have three different reactances? That's the explanation. So in order to keep the voltage at 1 per unit, when in reality, it's the voltage that is decreasing in value. So, yep. Some tables from the IEEE, they have some recommended values here for generators and machines, whether it's remote or local, and values of reactances, depending on the number of poles of the machine. So yeah, I'll just pass this as a reference so that we don't have to deal with it too much. So induction motor, how do we model that? As mentioned. Now let's see here. So you have here your XR value and your XD double prime. So this is SKM. And ETAP, there is more information. They would show the XD double prime and the XD prime. Or that may be for the synchronous motor. Okay. Some data. So cable, transmission line, transformer reactors are essentially impedances. So they limit your fault current. They don't contribute to the fault, they limit the fault. That's what they do. So assumptions and system modeling for short circuit calculation. So as I mentioned, the voltage is assumed to be balanced and under constant frequency. See, the source driving voltage, this is taken from the IEEE. So that's the same thing that I mentioned earlier. So we keep the source voltage at the same. And fault impedance is neglected. That's the arc fault impedance. And like so that's very difficult to predict. So synchronous and induction motors may vary in magnitude upon the inception of short circuit. So yeah, that affects your at which time you're interested to analyze. So I said during the half cycle, you have everything is contributing to the fault, and then 1.5 to 4, your induction is gone. And then 30 cycle, all motors gone. Let me just pass through here. Okay, so this is the one I was talking about. So first cycle duty, that's your half cycle essentially. Interrupting, that's your 1.5 to 4. So applicable to medium and high voltage circuit breaker. So why is that? So circuit breakers, the medium and especially high voltage breakers, they are rated 3, 5, and 8 cycles. So that is the operating time of this breaker. What does this mean? So it means that it takes this much time for the breaker to open totally quench the art. That's why when considering, when specifying these devices, we look at this 1.5 to 4 cycles. But for fuses, MCCBs, the one that are very fast, you have to look at the first cycle duty, first cycle current. Of course, the steady state or 30 cycle, that's your you have to consider that for your time delayed devices. When you do your time current coordination, there will be delays in let's say, just for analysis, right? So normally we're talking in seconds here. So the fault, let's say that's your fault current. This is now normally in seconds, not half second, even longer than that. So you could say that now you have to deal with this fault current, which is lesser than your first and interrupting current. So that's why it's important to know which network are we talking about, for what kind of application you're using it for. So using for time delayed devices, time current coordination, you know that you're talking about 30 cycle or more, because the time current coordination alone for time TCI, time current interval of or CI, coordination interval, I mean, for your relays, let's say, it's already specified in 0.3 seconds. That's already a long time. So what is a 30 cycle? 30 cycle is what? Half second, 0.5. Okay. So that's in that region already. That's past your zero point 0.4. Not to mention that you have some inherent delay here. So just wanted to bring that out, that you have three different network when you are analyzing for your fault currents. So here is your first cycle calculation. Yeah, momentary rating. That's when it's we're talking about here your the withstand rating of your, let's say, MCC or switchgear. So same idea. The calculation for your first cycle, your interrupting, and your time delayed, they're the same idea, the same thing that we showed earlier. The only difference is that you are changing the impedance of your motors. That's the only difference. In fact, when we model here in ETAP, let's say here, we have this example of first cycle here. We're asked to analyze the first cycle, which is the peak, and interrupting short circuit currents at bus 7 here. Fault is here. And we have the data of your utility, transformer, and your induction motor. So don't worry about this numbers here. Don't worry about that. So what we do during fault, you will have contribution from above and you have contribution from your motor, right? So that means you have to add up your utility impedance, your transformer impedance. They are in series, so that is this portion here. Z T3 plus C U3. U3, that's your utility, and T3 is your transformer. You add them in series. And then your motor is also contributing from down below here. So what that tells us is the motor is connected in parallel. So that's why your equivalent Thevenin impedance is looking like this. So a motor is in parallel with the series combination of your uh, utility and transformer. In other words, if we draw that, let's say this is your source, your utility, this is your utility impedance, this is your transformer impedance, and this is your motor impedance, like that. During normal operation, they're connected like that. During fault, the fault happened here. This is where your bus 7 is located. So your utility will contribute to the fault in this manner, while your motor, because temporarily your motor will act as a generator during fault inception for 2 cycle or so, it will contribute to the fault like that. And then your fault current is this total. This is your I total. So this is a contribution from your source, let's say, and this is the contribution from your motor. So that's why when you look at it, if you fold the connection from this point, they're connected in parallel. So that's why our expression here, this part is this. They are in series, and this M3 impedance, the impedance of your motor, is connected in parallel here. So you just have to look at your points of interest where the fault is located. So now suppose, let's say, the fault happened here instead. So in that case, you will rearrange your impedances. What happened here now is, well, your Thevenin equivalent is equal to the series combination of your transformer plus your motor in parallel with your utility. So then this whole thing obviously is 1/. So it depends where your fault is located. So as you can see, it becomes very tedious if you want to look at want to calculate at every point. So now having said that, so we have tabulated all of the we obtained from the data here given to us. We would add the R value, the X value, and the Z, and then we change to from the old base to a new base. Okay, so I'm not showing here the calculation. So and then we would sum up U3 and T3, the utility and the transformer here, because they are in series. And then this one here is essentially where we were trying to, because I use the Excel uh, to arrive with this calculation so that I could show you something. So I inverted the motor because it's in like our formula here. That's this one. So that's this value, and then essentially following on that formula, we arrive to this value. So this is the uh, total Thevenin impedance. So I have an R and X here, and my Z total is this 7.34, and I could also get my angle based on that 86.98 degrees. So what I need to do now is to get my base. I said I want 1000 MVE base. So my I base is essentially what? I base is equals to MVA base divided by square root of 3 times your KV base. So that is your 1000 MVA times 12.47 kV because the fault is happening here. That's why we're using that. It's easier to use that. That's the base current here. So now I have this 46,299, and then my I per unit is essentially uh voltage per unit, which is as the IEEE recommended to us, we use 1 per unit. Divide my Z per unit. So 1 divide this value here is 7.343132. So I have this value 0.013, and now simply to get the final uh, fault current is to simply multiply I base times I per unit, and that's what we did here. So these two multiplied together is this one. And when we compare that with our ETAP calculation, 6.303 kA or 6,303, and we have obtained 6,305. Very close to account for some iteration of software, which the uh, Excel cannot do. So that's good enough. 3 amps is not a big deal out of 6,000 amps. So that's how we do the calculation that involves per unit transformation. So that's for the half cycle. Now let's do a 4-cycle calculation. 4-cycle, 1.5 to 4 cycle. So this is the interrupting region. So same idea, but as you can see here, let's see here. Just notice that during half cycle, there is 515 amps, 0.515 kA contribution from the motor. Now that we're in the 4-cycle network, this is now 344. It reduced. Why? Because when you go back here, induction motor, when you go back here, you can see in this, I don't know if it's visible to you, it's kind of small. you can see here that for the half cycle network, it's 15.385%. And for a 1.5 to 4 cycle network, it's 23.077%. So as we have said earlier, uh, as time passes by from half cycle to 4 cycle, we are now entering the uh, x prime, xd prime. So this is your xd double prime. This one is your xd prime. So transient, this is now your transient. This is your sub-transient. So higher higher impedance, which obviously would result to lower uh, fault current. So that's why using the same steps, no difference, same steps. We did the same steps, but now the motor impedance has increased. It affected its contribution. So now before you have 6,305, now you have 6,133. So there is a reduction of what, 200 amps something. So that's the difference. Now here we're now entering the 30 cycle network here. Same idea, same calculation. But this time what happened is the motor has no more contribution, no longer contributes to the fault. The fault contribution is solely coming now from your utility. The motor field has totally collapses and is no longer contributing fault current into the system. So here, just for the sake of calculation, I should have just removed that from the network, that motor. But in order to account for, just to show here that we're still using the same formula, I just modeled the motor impedance as very, very high or infinite impedance. Essentially doing the same effect. So very, very high impedance means open circuit. So we now have 5,790 amps in manual calculation, or 5,787 using it. So now we can clearly see here that the transition from half cycle, which is the highest fault magnitude, to the 4 cycle, which is slightly lower, and to the 30 cycle, which is the lowest steady state fault current, at which time only your utility is contributing to the fault. Okay. So here, this one is essentially this one. So it's easier to look at here. So for equipment evaluation, we would evaluate fuses, high voltage breakers, switches, switchgear, recloser, almost all of them. We try to look at the first cycle current. Breakers, some breakers are normally comes with they are normally rated in symmetrical rating, but when they are tested in the laboratory, they are subjected to certain level of XR ratio. Typically, I believe 17 is the XR ratio. Meaning that breakers have been tested to a certain level of asymmetrical rating, which I said, I don't know if I have it here. Let's see, high voltage breaker. So you have S factor is not the same here. I don't think it's here. S factor. I'm not sure if that's the same thing. Uh, um, um, 1.1031. No, that's not the same one. So in the data sheet, they would specify at which power factor the breaker was tested. So meaning, like I said, the breakers or your high voltage breakers, your reclosers, even your MCCBs, they are rated for a certain level of symmetrical and asymmetrical current. And I'm going to show why that matters later on. So, okay. So here, we'll look at if breaker 19 and 22 are adequately rated with respect to the short circuit currents. So here we have the value of CV19 and CV22. Now that's the same breaker in the previous diagram. So now we're using this expression. We will calculate. So I have some lookup table here that doesn't link anymore. I'll find it and send it together with the notes. So now here tabulated. So our C again. Do I have the okay? It's a bit far. So that was this breaker, this and this. So that's the one we're trying to evaluate. Okay, here it's clearer. So that's CB19 and CB22. That's the one we're trying to evaluate here. So for CB19, so I have tabulated here already. So the first cycle, 60 16.73 is the RMS, 85.5 the peak, short circuit is 46. So let's compare that with the rating. This is actually the rating that we're trying to compare with. So 31 and 1673. So it's 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 meeting. Obviously, it's meeting because I only modeled a few of them, but that's the process. When you have the actual installation, obviously you have more than just one motor, right? So it adds up. So you have more devices. So this is not a realistic example because I modeled only one motor for simplicity. So now when you are evaluating an actual project, obviously, you have a lot more contribution from different sources. So the comparison is not realistic. So it's very low compared with this one, because like I said, we only have one contribution. So it passed easily. But mind you, when you have hundreds of motors in your facility, they all add up to thousands of amps. So maybe that will not pass anymore. So regarding the just I want to dedicate this part to looking into the XR ratio. How is that in any way uh, related? So kind of mess up my it kind of mess up my presentation here. So the manufacturers would publish uh, tables for which XR ratio they have tested the devices for. Like I said, so and then you'll have to compare that. You have to derate your device based on the actual uh, XR ratio that you actually have in your um, fault. So let's say you have a breaker uh, with a rating of okay. So here, these are just some of the things that you can do to lower your uh, available fault. You could install a series reactor or a current limiting fuse, or you could this designing the utility, you designing in considering the utility as an infinite source. You can only do this if the project is at the design stage, but if it's an existing project, you cannot do that, obviously. What we're saying here is in order to be safe, um, which is, I would say, not recommended all the time, but when you're in the field and you're trying to estimate whether the equipment is capable or not to handle the the fault magnitude at that location, let's say a transformer, uh let's say an MCC connected directly at the secondary of the transformer, you can use this infinite pass uh assumption. What that means is essentially you're saying that the source or utility has zero impedance. So your fault current is only limited by um, your transformer impedance. So, and that is I'd say a conservative approximation that you can do immediately uh, cite. But during design stage, I would say if it's a brand new project, then gather all of the uh, data as much as you can to make it a more realistic design. So I would not, just randomly recommend to, because if you assume an infinite source, maybe you are oversizing your uh, devices then. And I'll do an example, but let's see. Let me just do that. So this is related to that concept. So um, this is in the transformer. So I have here some actual transformer test result. And in that report, so you can see the impedance here, here. So these are different test reports. So measured impedance, and they show us the voltage, even the top positions. That's normally in the mid. Top 17 is the mid. So how is this test normally conducted? So essentially, you short circuited the secondary, and then you apply a voltage here, and then this voltage, you would vary it. You increase it. You begin from zero, and then you increase it gradually until such point that rated current flows through the secondary. And when that happens, you mark that voltage, whatever that V test voltage, and that V test voltage, when divided by the V rated, is essentially equal to your percent impedance. That's equal to your percent impedance. In the old days, it's called impedance voltage, because they came from this idea that it's a voltage that is a ratio of the rated voltage. And that may sound kind of confusing. Why is the voltage divide voltage equal to percent Z? But remember that percent Z is actually dimensionless. It doesn't have unit, not ohms. It's a dimensionless quantity. So if if we dissect further, so V test is nothing but uh, I rated times Z, C ohms, which is the per unit, which will become the per unit ohms eventually. So if we divide it with V rated, which is again equal to I rated times the Z, which the apparent impedance of the transformer. Now this cancels out, and now you have left with a ratio of the impedance in ratio to an apparent impedance. So that's essentially a dimensionless quantity. So that's why in the old days they call it impedance voltage, and now we just call it percent impedance. So here's an example of infinite bus method. So here we'd like to calculate the available fault current at the secondary of the transformer using infinite bus method. And here is the data of the transformer. So, that's done. So essentially, in order to basically do that, is will just divide the 3750 kVA divided to 3 times secondary is 12470, and this is become your I rated, which is or full load current. So that will become what? 3750 which is 173.6 amps. And then simply to get the fault current is 173.6 divide your per unit impedance, which is now 0.066. Yeah, 0.066. So now you have 2630.6 amps. So you can see that here in this calculation, unlike the previous one, we did not include the utility impedance. We assume that the utility impedance has no value, right? Zero impedance. So, but then the issue here would arise that, let's say this is your transformer and it's connected to a panel, let's say. Because you did not include your utility, you might be over estimating your fault current. So now imagine that's just for 3750 transformer. What if you have a bigger transformer here? Which means your your fault current will increase also because it's a function of your kVA, your kVA rating, your apparent power rating. So two things two things here that I would say is a consideration here, that things to things to notice here. Just because you can specify a transformer, a bigger transformer, doesn't mean you should do that, because it kind of it kind of, I should say, a a default answer. Eh, when you're designing something, you would say that, oh, I'll just put something bigger here so that uh I'm safe. I will not overload this transformer, making sure that I'm not overloading the transformer. I'll put something big here. And just because you're able to put a big transformer in there doesn't mean that uh you should do it, because what it does is increasing the available fault current in that point. And the other one is, without considering the utility fault, the utility impedance, you have increased your calculated short circuit current at that point. So the recommendation again is to as much as possible get your data, as many relevant data that you can, especially your utility impedance, because that will, you might find out that when adding your utility impedance, actually you only have like what, 1000 amps maybe when you add that. So now you're able to specify a lower rating for your MDP and for your breakers, and you could save money by doing that. You have a more realistic design. And but on the other side also is the consideration that, like I said, like I mentioned earlier, do note that utilities over time would tend to increase their capacity, which means increasing the fault level at that point. Okay, so let me now do something. I should have put it in the slides, but somehow it did not save. So we did infinite bus calculation, we did transformer, utility, and we did cable uh, calculation. We also did motor. We kind of covered everything, I think. Uh, Short circuit testing. Okay, let me do this one thing here. I don't have any space. Let me just do it here. So this is related to the XR ratio. Well, this is not the, okay, let me put it here. It's kind of relevant here. So suppose we have a breaker rated 65,000 amps interrupting. And so let me see. This is CB interrupting rating. Okay. And then that's data number 1, data number 2. And then we have a short circuit current, short circuit amps that is equals to 62,000 amps. And then the XR ratio, data number 3, at that fault location where the breaker is installed is equal to 11.72. Let's say this breaker is tested let's say I'll just put it here. The breaker is tested at XR ratio of 6.6. 6.6. Okay. So the breaker is tested at 6.6, and while the actual XR ratio at that faulted point where the breaker is connected is 11.72. So the question is the breaker adequately rated to interrupt this fault current? So within one look, at the first look, you'd say, well, I have 65 versus 62. And then, yes, good, I'm good. I'm okay. The breaker is properly rated for that application. But then we forgot that the manufacturer of that breaker has published a multiplying factor for that application, basically saying that if the XR ratio at that faulted point is 11.72, then you must multiply your short circuit current by a factor of 1.09. I'm looking here at my notes, so you're not seeing that because for some reason I woke up at 2 a.m. and then I tried to add these remaining slides and then I saved it, I closed it, and now it's not here. I don't know what happened. So sorry. Uh anyway, uh for this XR ratio, we are actually supposed to multiply it 1.09, meaning actually my peak current, this goes back to your asymmetrical current that we were looking at earlier, a lot of graphs in there showing you how important it is. It's actually, my I peak is actually 62,000 times 1.09. And if I try to solve that, I would get 67,580 amps. Now suddenly it's 65 versus 67.58, which means my breaker is not adequately rated for this. Where did this thing came from? 1.09. Well, that is published by manufacturers. I was gonna show you a bunch more of data, but they would normally publish what we call a multiplying factor. So I'm just gonna show you. Let's say for a 4.9, this is your XR, this is your MF multiplying factor. For a 4.9, multiplying factor is here, one per unit. For a 6.6, is one per unit. For an 8.27 is 1.04. For 9.95 is 1.07. For an 8.5, oh no, for okay, 11.72 is 1.09. This is where it came from. The test power factor for this particular breaker, and you have to look at, this will vary per manufacturer, per model of the breaker, so you cannot guess this. This is something that we cannot guess. So the test power factor is 6.6, although I would say that they are governed by the IEEE standard. So they would try to use what the IEEE has recommended, but it has some variation. So it's not an exact science. So try to look at the actual breaker data sheet. But what I'm trying to drive at here, why I'm keep going back to this 1.09 here. Where did this came from? So remember I showed earlier, let me try to bring back that, and this will be, let me, 1 second. Maximum peak. Okay, so this goes back to the formula earlier that the half cycle equation is essentially, I'm running out of place to write. So the half cycle, let me write here. A half cycle equation, I peak is equal to IAC peak plus IDC, which is also equal to square root of 2 times IAC RMS 1 plus E raised to the negative 2 pi T divide XR, X over R. Okay, so looking at this expression, and we said half cycle. So the time is equal to 0.5. So 0.5 times 2 is essentially 1. So we could reduce this expression to, I'm just going to write this part. We could reduce this to 1 plus e to the minus pi over xr. So this term here, this term is influenced by your XR ratio. Now we said that this manufacturer has tested a breaker at 6.6. So looking at this expression, I would plot one, I would put 1 point e to the negative pi divide 6.6, and that is roughly equal to what? 1 plus e raised to minus pi divide 6.6. That's 1.6212. Now using the actual XR to the negative pi divided by 11.72. That is 1.7648. So as expected, the higher the XR, the higher the total fault current, right? So if we divide this to 1.7648 divide 1.6212, you have 1.088. That's your 1.9. That's your 1.9. Try to do that for all of this remaining terms, and you'll find that it corresponds to that multiplying factor. That's where it came from. So in a way, what we're trying to emphasize here is you are adjusting your fault current using the actual XR ratio and compare it with the actual well, let me rephrase that. You are analyzing your fault current in the peak region, the half cycle region, so you get your asymmetrical peak, and then you also have to express your interrupting rating of your breaker in the same time frame, the same time domain. So using the XR ratio of your breaker, obviously that's your 65 times 1 plus e to the minus pi over 6.6. So we just omitted this part because uh, that's no longer necessary because it will cancel out, right? If you divide that if with the same term, it will cancel out. So we did not put that anymore. It's not necessary. It will cancel out. So we're only interested in this term because this one remains. So when you divide the resultant, you get this. So what we're saying here is uh, don't just look at um, the RMS value when you're dealing with circuit breakers, and say that, oh, uh, symmetrical 62, symmetrical 65 versus fault current symmetrical 62. I'm good. So we'll have to look at the asymmetrical fault level when it comes to our breakers, because again, as mentioned, why we're interested with that is because during this time, this is the time when these devices, these breakers, are trying to interrupt a current that is actually not just consisting of your symmetrical AC, but it contains the decaying DC part. So it's just fitting. It just makes sense to consider that decaying DC part in your calculation, in your half cycle calculation. That is because that is when your uh, breaker is trying to separate the contact, trying to open the contact and trying to interrupt that match magnitude. Imagine the difference here between 67 and uh, 62. It's quite significant. That's 5,500 amps. So it's quite significant. So now imagine if this fault has occurred in the terminal of a generator. So in a generator, typically, in the terminals of a generator, typically the XR ratio is 40 and above. So imagine that 40. This is only 11.72. And your multiplying factor is 1.09. So imagine a 40 XR ratio. So you could already get the picture, right? So consider that one. So the other one that I have the unfortunate incident of did not saving that slide. The other one that I'd like to talk about is the current limitation. So I mentioned here, why do I keep doing there? So here, I mentioned here, what else can you do? Well, you can install a series reactor. It's one of the things. So what does a reactor do? It chokes out current, essentially. It opposes the change in current. So it's an impedance, essentially, if you think about it. So what does impedance do? It brings down current. So let's say you have this old facility and it's all rated in 40 ka, 40,000 amps. All of your MCC in your entire plant, you have hundreds of that rated 40 ka. Now suddenly 10 years later, much has happened in the vicinity of your factory. Lots of residential areas have came in, lots of other factories have joined in, and you know uh, suddenly you woke up one day, your substation 10 years ago was 50 MVA. Now it's 200 MVA. Meaning your your although that's kind of an extreme example, right? Because it doesn't happen overnight. Like I said, every 5 years or so, we are mandated to do a study to analyze what has happened, whether the fault current is increased. But anyway, what I'm saying is, now you are facing this situation where the fault level in your area has increased, and now your devices, your switch gears, your breakers are no longer suitably rated to withstand that magnitude. So what can you do? You can install a series reactor. So what does the reactor do? It's essentially an impedance. So what happened with we said that, you know, a utility is just a series, a parallel main of an infinite number, n number, not infinite, n number of uh, impedances. So they have added more and more generation, meaning more and more impedances, brings down the impedance, increases the fault current. So what you can do, install same amount of impedance to bring it down. So that's what essentially your reactor is doing. You're increasing the impedance, bringing down the um, current, fault current. The other one is current limiting fuse. So what current limiting fuse is essentially, uh, let's say this is your fault current. So that's one cycle, let's say. What current limiting fuse do is the inside the cartridge, it's surrounded by some type of material that when the the fusing element, the metallic element melts due to the high magnitude of fault current, that material, it's believe a silica, uh, gets exposed to that high magnitude of current. It crystallizes very fast, and it offers a very high amount of very high value of impedance. And what does that does is essentially choking the current. So, and it acts within quarter of a cycle, essentially in this region. So uh, it instead of having your fault current to go through the final peak, this value, it chokes out the current, so that at this point your connection is already severed. You're no the fuse element is already severed, and beside that, the arc is quenched, because that material offers very high magnitude of resistance, and instead of being able to go to the peak, now you are here. So it greatly reduces the amount of fault current that it allows to pass through. As an example, a current limiting fuse rated for 240,000 amps would only allow 100,000 amps to pass through. So you could see that it's even less than half. So it reduces the fault current to less than half. So of course, when you are specifying this, make sure to look at the data sheet. Again, make sure that what you're uh, selecting is appropriate for the application. The other one is obviously replace the equipment with higher rating, but then again, your client may not like that because that means higher cost. But if it's really necessary, then well, what can you do? So I just have a report that I submitted last week, which is exactly this. So I don't know what happened with that facility. So a lot of their devices are rated 35 kA. I did the report, the study uh, last 2 weeks ago, I think. So most of their devices are passing the analysis, but there are like 21 devices that failed. Some of them are 14 kA, while the available fault current at the bus where they're installed are 35. So I said, you know, this needs to be replaced. I mean, uh, you guys have to replace this because it's definitely not passing the the calculation. So maybe what happened there is they have installed, somebody just installed it without looking, because it's kind of obvious. All of the other devices, I mean, not all, most of them are 35 kA and above, while these few pieces are 14 kA. So somebody must just have get something from the hardware and just put it in there. Oh, it fits without doing analysis. So that's one thing. Okay, we already talked about utility as an infinite source, so that's done. Series rating is uh another. This is related to the current limiting fuses. So series rating, what it is all about is essentially when you have a device such as a breaker, let's say, that is not passing the calculation. Let's say you have a breaker here that is not passing the rating, the calculation. Let's say this is a 14 kA breaker, and this is, let's say, have 40 kA fault level in that bus. So one thing that you can do is obviously replace the breaker, and the other one that you can do is install a current limiting fuse here. A fuse that is capable of uh, interrupting this 40 kA. Fuses are normally have very high rating, especially current limiting fuse. They are in the order of 200 kA, 100 kA, 200 kA or more. So it's not almost an issue. So what happened here with uh, proper selection, and there is manufacturer's recommendation here to be followed, by the way. So there is a published document by manufacturers when you're trying to use a series rating. So it can be a breaker and a fuse, or a fuse and another fuse. Well, if you use two fuses, one of them is current limiting and one of them is obviously not current limiting fuse. So there is some published document per manufacturer that they will tell you that, let's say, an F-frame breaker would you can use, let's say this is an F-frame breaker, and if you wanted to use a fuse upstream and it's a class R fuse, you are allowed to go as 400 amps. That's your maximum. So there is a table. I forgot what's the name of the table, and I even forgot to add it here. But anyway, there is a table that each manufacturer, you have to consult the manufacturer. They will tell you. You actually try to Google it. Go for uh, Peraz. It's one of the, or Square D. They have tables in there that shows this size of fuse or breaker works with this size of current limiting fuse. And there's a ratio, let's say 2-to-1 ratio, 4-to-1 ratio. So that is something that you can do. And then with this combination, your breaker is considered to be able to be protected. So your fuse is essentially protecting your breaker here in this case. So your fuse will act as a the one to interrupt the very high magnitude, and so your breaker is now able to, because it reduces the fault, right? Based on what we say here, it reduces the fault level considerably, and now your breaker is able to interrupt that reduced fault current. So your breaker is now considered suitable for that installation. What else do we have here? So panels can also be there are also series rated panels, but they must be UL tested combination. So they have to be certified by UL. So what happened with that series rated panels is essentially you have, let's say, a 22 kA main, and then you have 10 kA branches. Normally, what I see most of the time, normally, all of the breakers, the main including the branches, they are normally rated to be the same, and the panel also. So what you would see normally, if let's say the panel is rated 32 kA, let's say, you would see that your breakers are either rated 32 also, or they are a little bit higher, maybe 40. So, but this series rated panel is a UL tested, so that's why it it allows you to install the lower rated branch circuit, because they have to be coordinated again, just like this fuse and breaker scenario here. They have to be coordinated such that the main branch, the main breaker is able to protect the branches. But personally, I would select the fully rated. When we say fully rated, all of the breakers are of the same rating, same, including the panel. I believe we have covered the things that we need. We have any question? Let me see here.
Hi, sir.
Hello.
May nakita po ako kaninang question from Sir Donaldo Organo. Ask lang daw po niya, sir, kung kailan gagamitin sa computation ng short circuit ang 1/2 cycle, 1.5 to 4 cycle, and 30 cycle.
Okay. So Thanks for that question. So, kailan gagamitin? So, as I've mentioned earlier, so I think here. So, for equipment evaluation, I think this one is even clearer. So, for equipment evaluation, fuses, we said we want them to be evaluated against the first cycle because uh, they would interrupt in that time frame. The fuses are very fast, so half cycle maybe even less. So that's why it only makes sense to evaluate these devices in this region. High voltage breaker. So I said breakers are would interrupt the current at around, well, it depends on the breaker design. So you have now you have 2 cycle, but commonly you have 3, 5, 8 cycles. So 2 cycle breaker would begin to interrupt, would the contacts would begin to separate 1 cycle and another cycle to totally quench the arc. So that's your 2 cycle breaker. Although it costs more. So, but I have a project I'm working on right now that is a 2 cycle breaker. In the same manner, 3 cycle, 5 cycle, 8 cycle, it takes this much time to uh, interrupt. So that's why we're saying here that for breaker, you may want to measure it against the first cycle region and the interrupting region because there is variation. There is some variation with breakers. But well, obviously, if your breaker has passed your first cycle and interrupting, then it passes your steady state time delayed because this is lower, obviously. So same thing with your switch gears. I said the switch gear and the MCC must be able to withstand the vibration, the mechanical vibration uh, brought about by the peak current. So that's why we want it to be measured or tested, or not calculated against the first cycle. Same thing with your recloser and transformer. Obviously, transformer gets subjected to uh well, to all kinds of fault current, really, from first cycle up to the steady state. But the worst case being your first cycle. When it comes to relaying, well, well, fuses is also part of relaying. By the way, your time current coordination. I'm referring to the time current coordination. When it comes to that, well, depending on your coordination interval, as I mentioned earlier, you may have to uh, look at for cycle and steady state. But for your fuses, very fast acting, and even now there are relays like this Schweitzer relay. They can make tripping decision within less than a cycle. So yeah, you still have to evaluate them at the first cycle. That's okay. CT. Oh, I did not mention about CT. The CT, there is a the CT is normally, well, we evaluate the CT based on the rated current, right? Your 1200 to 5, let's say, should be able to withstand, should be able to carry 1200 amps continuously. But then where it becomes relevant, the XR ratio, this goes back to the XR ratio really, uh, where it's relevant for the city is during the first cycle where you have DC offset, meaning your total peak current is uh, heavily uh, influenced by your DC offset, and it's the asymmetry is great. It can saturate your city, so you'll have to you'll have to consider that in your uh, calculation. I actually covered this in another training that I conducted in industrial protection. But anyway, I'm saying is um, the asymmetrical uh, magnitude, which is heavily distorted, greater than your symmetrical current, could saturate your city. So you have to select your city in such a way that uh, it's rated to withstand that. And why is that an issue? So the issue is when your city is saturated, it does not behave linearly anymore, meaning it does not give the correct information on the secondary. So, and there is a curve that we call a knee point. So it looks like this. So for the first, and this is what your knee point. This is what we call your knee point. At this point, your city is not behaving linearly anymore. So when we say linearly, this is your region that behaves linearly, meaning the magnitude that it sees on the primary, it gives the equivalent transformation on the secondary. But past this part, you can see here that uh, an increase in the current in the primary does not result to an equivalent increase current in the secondary. It's not linear anymore, meaning you're giving false information to your relays. Because what is a city? A city is just your eyes and ears for your relay. It's the one that gives information to your relay. So when your city is saturated, it does not give the correct information anymore, meaning your relay will not function properly. It may not be able to detect the fault correctly and would not be able to make a correct tripping decision. And as I mentioned, relays, especially digital relays nowadays, are able to um, make tripping decision within one cycle. So again, it's in that region where the asymmetry is the greatest value. It's in the first cycle. So during that cycle, your relays are trying to make the tripping decision, but it could not because your city is saturated. So that's why we're interested to uh, size your city based on the first cycle network. Did that answer?
Okay po. Sir, next question po from A83 ano talaga yung name niya. So, tanong po ay, ask ko lang if kung ang building ay merong solar panels installed that is grid tie, should I also add its maximum current capacity to the short circuit current source? Thank you.
Oh, okay. Good question. So I'm working on a solar project. Yeah, it 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 does add, but solar generation facility is a weak source. You know, it's a weak source of fault current. It's not it's not the same as your it's not the same as your utility. Obviously, it does not. Even our I have this I'm working on a project right now, which is a 400 megawatt solar generation facility. So one one panel is like 50 amps. It's very small, 50 amps. But we have like more than 3,000 of those. So they add up together. Oh no, not more than 3,000, more than 100,000 all in all in the facility. So they add up together. So but then you said it's a residential area, so I don't think it really would create a lot of difference. But you know, how much is the capacity of that? You could probably approximate. It's not like your the thing with solar, the panel itself, the fault current that it generates is almost the same as your rated current. It's not like your motor where your fault current, where the fault contribution of your motor is like 6 times of your full load. So your solar, the fault contribution of your solar is basically what is your full load rating of your solar panel, your cell. So yeah, I would say you if you can try to accommodate for that. But yeah, I that's the best answer that I could give, I think.
Okay, sir, next. From LM, in building design, assuming the building will be leased by mixed-use tenants, that is office, retail, and restaurants, what would be the assumption of the tenant space for the impedance diagram, given that you don't know what will be the load of the space in the future?
Mm, yeah, yeah, that's difficult. So that's difficult. So uh did you say residential and commercial,
Ano
right?
po ito, sir, tingin ko parang mall, mga mixed-use yung tenants, pwede rin mga office spaces,
So
mga
industrial
tenant.
facility, sorry. So industrial facility, we normally estimate 80% of the load to be motors. So based on that, you can estimate how much fault current it contributes. For a commercial and industrial especially, no, a commercial and residential of office, I would not think that they have a lot of motors. Remember that the main contributor to fault is generator, utility, and motors. So maybe you could estimate that for for a mall or an office, 30% motor, or maybe less than 30%. So but try to look at the panel schedule, to the load schedule, and you could approximate. And you're only interested with the motors because that's the only one contributing to the fault current. And for load growth, it's hard. It's hard to predict the load growth because I don't know what the mall owner would do, right? But I guess I don't know. Look at how big is the building. Maybe I'm not expert in building design, by the way, in commercial. So maybe look at the size of the building at this time. Maybe uh how much percentage of the building is occupied, and in the future, well, they could only go as far as occupying 100% of the building, right? Unless they build another building on side that. But that's that's be- that's beside the point, I guess. So the main thing that will influence your fault current there is the utility in that case, I think. So in the utility, increase the size of your transformer serving that facility, or increase the size of the substation, then that's really the thing that would make a huge impact. Oh, there's a question. How about multiple motor connected on one free air distribution line? Will I add individual short circuit per unit para sa main? Oh, yes. So, yeah, each motor will contribute to the fault. So you have to add them, especially if there's a lot of them. So yeah, it goes back to what we said here. So earlier I only show one motor, right? So but if you have multiple motors, you have, so from your utility, all of them will contribute. So you have to consider them.
Sir,
Considering, oh, go ahead.
Okay na po ba? Tapos na po ba yun? Yung question. May nalagpasan po tayo. Mula po kay
Yeah.
Sir Edwin Roldan, where are we going to base the short circuit rating of the breaker? Is it the line to line to ground, or three-phase fault?
Three phase. So normally when you conduct analysis, you have to do two types of calculation. Three-phase fault, which is normally the severe fault with some rare exception, and one single line to ground. Normally the three-phase is the highest with some rare exception if the fault happens to be at near the terminal of a delta wide transformer. So that's sometimes, depending on the construction of the transformer, it can be a little bit higher than the three phase. The single phase can be a little bit higher than the three phase, just a little. That goes back to the symmetrical calculation, which is not part of our topic here. Oh, by the way, if you're interested, I'm doing the symmetrical component course in August. But
Ayun,
anyway,
maganda yun, sir. Invite natin sila doon sa pa-web sa seminar mo. Training on Parang meron ka po ata, sir, July, or June ba yun?
minob ko sa August kasi
August.
humaba kami ng humaba sa industrial protection. Kala ko
Opo.
tapos sa March, inabot na ko June.
Ilang sessions po yun, sir, yung inyong industrial protection?
Ang in-advertise ko for, abot kami ng 12.
Maganda yun, sir.
Yeah.
Talagang ma-explain in detail, kasi importante ang bawat detail. Okay, so mula naman po, sir, kay Dante, Sir Dante Cervantes. If meron po old industrial plant na main circuit breaker niya is low voltage MCCB, pwede po ba itong malagyan ng mga relay for protection coordination purposes?
Yeah, in general, yes. Normally sa mga facility naman, o sa mga industrial installation, there's combination of things there. So normally you'll find fuses, breakers, and relays all together as a facility. So for example, ang smaller motors, you'll find a combination ng breaker and starter. And then yung medyo malaki ng kaunti, may fuse and may breaker pa siya. So, and then doon naman, normally ang relay makikita mo sa medyo malalaking motor like MV, and then protection sa transformer, normally makikita mo ang relay. Just because simply yung relay medyo mahal siya. So, hindi naman justified na bumili ka ng uh, I don't know, $3,000 na relay para protektahan yung $500 na motor. So it's not justified. So, but in general sa facility, makikita natin yung combination ng relays, breakers, and fuses. But to the question, I believe if I understand the question correctly, is it okay to put a relay in an old existing facility with old breakers? I don't see why not. But the only thing that you have to consider is obviously you have to uh bring up and get the curve characteristics of your existing devices, and then you have to conduct a device coordination study and try to coordinate that with your newly installed relay. So we do this. May mga project akong ginawa na luma na eh, minsan minsan mahirap siya kasi minsan legacy na yung breaker, hindi na nila mina-manufacture ngayon. But luckily minsan makukuha mo pa rin naman siya sa database ng ETAP na meron pa sila dong mga legacy. If not, try mong hanapin yung closest model na may kaparehong curve characteristic doon sa mga old relay. Sa mga old breakers, I mean. Sa mga bagong breaker, no, madali. Walang issue. Mahahanap mo kahit sa online ah yung yung ano nila, mga TCC.
Okay po. So next, sir, we have from Sir Jeffrey Bautista. Considering the fast progress happening here in Palawan, would it be safe to use the infinite bus method, also taking into account even when we request data from the utility, their database is not updated?
Hard question. Right now, ano ba yung fault level diyan, let's say?
By request po, sir, kung sa ano ko, nakaraang paggawa ko ng mga studies, nare-request siya sa Paleco Palawan Electric Cooperative. Pero di ko po sure ngayon kung nare-request pa.
Dati mga ilan yung value? 100
May nakuha ko
MVA,
dati parang
1,000.
86 MVA at a certain certain
86.
location. 6.4 MVA SC.
Okay. Anong voltage level nun? Mga
13.2 po.
15?
13.2.
13.2? 15.2. So, well, kung ilagay mo siya sa 100 MVA, interested lang ako makita. 30 to 100. 4070 yung I-base mo. P squared. 1.74 amps, ohms. It's not hindi siya masyadong, kung i-infinite mo yan, I may have to look at it more deeper. But since you know na around 100 MVA siya in one location, well, you can make a good guess na around that ballpark din ang other location. So, kung gusto mo maging much conservative, well, you can add some safety factor maybe. Even bump it up to 200 MVA, let's say. instead of just ignoring it altogether and using infinite bus, and see if it makes a lot of difference depending sa application mo. So let's say using 200 MBA, you arrive to the conclusion na yung rating mo ay dapat, let's say, 30 kA. But then with using infinite bus, kung nag-infinite bus ka, it can happen na lumagpas ka na sa available rating. Let's say umabot ka na ng 85 kA. Well, I would recommend na gamitin mo yung good guess mo na lang kaysa sa hindi ka na makapag-design, right? Or I mean, mapilitan ka mag-install ng current limiting fuses, and you'll have to explain that to your client. So I don't think they're gonna like that. So yeah, it goes back to different engineers has different answers. So I don't have the answer to everything.
Sa Palawan, sa akin, parang 300 nga ata yung ano ko eh. Pag hindi alam yung, minsan kasi hindi mo makakuha rin sa utility. Parang safe na rin na 300 yung ano,
Yeah.
utility. Kasi wala ano eh. Tapos, ay sir, may request po tayo from Sir Joel Benavice. Sir, can you share your presentation via email or their copy? So siguro
Oh, sige.
po, kung bigyan niyo po sa akin, sir, ako na lang po mag-send. Papunta
Yes,
sa
sir.
emails.
Forward ko, medyo linisin ko ng konti. No,
Sige
kasi
po.
may update akong ginawa kanina, hindi na nawala.
So, opo, pag nag-send po kami ng certificate, so kasama na rin po yung ano nun, certificate. Certificate kasama na po yung presentation. Ayun. So na-upload ko na rin po yung sinend ko na po rin po yung evaluation form for the CPD. So para po ma-note po natin yung attendance and the evaluation po.